Before settling in, take a moment to like the video and subscribe to the channel. It helps more curious minds discover these relaxing journeys through space, and it supports the creation of future cosmic documentaries. Today's question sounds simple. How long would it really take to reach every planet in our solar system? The answer is far more surprising than most people expect. A trip to Mars can take months. A journey to Jupiter takes years. Reaching the distant worlds of Uranus and Neptune can require more than a decade of travel. And some destinations are so far away that an entire generation could pass before a spacecraft arrives. From the blazing heat of Mercury to the frozen frontier beyond Saturn, this journey follows the true distances, speeds and challenges of travelling across our cosmic neighbourhood. Along the way, it reveals why space is far larger than it appears, and why even our fastest spacecraft moves slowly against the vast scale of the solar system. Dim the lights, relax, and join this voyage across billions of kilometres as the remarkable reality of interplanetary travel unfolds. Now let's begin. The outer edge of the solar system begins with distances so vast that human intuition struggles to hold them in a single mental image. At this scale, Neptune stands as the first major reference point for deep interplanetary travel, not because it is the farthest object influenced by the Sun, but because it marks the boundary where traditional spacecraft journeys begin to stretch into many years rather than months. Neptune orbits at an average distance of roughly 4.5 billion kilometers from Earth, and that number alone becomes less a measurement and more a quiet expression of scale. Spacecraft moving along carefully designed trajectories do not travel in straight lines toward this distant world. Instead, they follow curved paths shaped by orbital mechanics, gravity, and the motion of Earth itself as it circles the Sun. The journey toward Neptune begins long before a spacecraft departs. Engineers wait for alignment between planets that allows the spacecraft to gain energy from gravity assists, most often from Jupiter, or sometimes Saturn. These assists act as subtle exchanges of momentum where a spacecraft passes close enough to a massive planet to be redirected and accelerated. Even with these advantages, the total travel time to Neptune typically extends beyond a decade. Some missions require more than 12 years to reach orbit or fly past the distant planet. This duration reflects not only distance, but also the need for energy efficiency, as launching directly toward the outer solar system would demand propulsion capabilities far beyond what current chemical rockets can provide. As a spacecraft moves away from the inner solar system, the nature of motion itself begins to feel different in a conceptual sense. The Sun's gravitational influence still dominates, yet its strength diminishes gradually with distance. Objects no longer accelerate in the same pronounced way they do near Earth or Mars. Instead, they settle into long, slow arcs that carry them outward, shaped by carefully calculated velocity adjustments made during the earliest stages of flight. Small course corrections made months or even years earlier determine whether a spacecraft will arrive within thousands of kilometers of its intended target. Communication also becomes a defining part of the journey. As distance increases, signals traveling at the speed of light require hours to complete a round trip between Earth and a spacecraft near Neptune. This delay transforms operations into a process of anticipation rather than immediate control. Instructions are prepared in advance, and spacecraft systems are designed to act autonomously, responding to conditions without waiting for direct intervention. The increasing communication lag becomes an invisible companion to the mission, marking progress not in real-time interaction but in delayed confirmation. The environment between Earth and Neptune is not empty, even though it appears vast and quiet. Sparse particles of dust and charged solar wind flow outward from the Sun, forming a thinning medium through which spacecraft must pass. While these particles are not dense enough to impede motion in a traditional sense, They represent the persistent presence of the Sun's influence even at extreme distances. As spacecraft travel outward, they gradually cross regions where solar energy weakens and temperatures fall toward near absolute cold. Instruments begin to adjust to lower light levels, and power systems increasingly rely on long-distance sunlight collection or onboard nuclear sources. Time perception becomes an important conceptual shift when considering Neptune-bound missions. On Earth, years pass with familiar cycles of seasons and human activity. In deep space travel, however, a decade-long journey compresses into a continuous, nearly unchanging arc of motion. There are no dramatic visual changes visible to the spacecraft itself during most of the journey. The stars remain fixed points of reference, and the Sun slowly diminishes in brightness until it becomes one of many distant lights. Only careful tracking of velocity and position reveals that the spacecraft is steadily moving outward through the solar system's outer regions. Neptune itself is not a static destination waiting passively in space. It continues its own orbit around the Sun, completing one revolution in about 165 Earth years. This slow orbital motion means that trajectory planning must account for where the planet will be years into the future, not where it is at the moment of launch. The precision required for this prediction reflects the complexity of interplanetary navigation, where both spacecraft and target are constantly moving through space in interconnected paths. When a spacecraft finally approaches Neptune's region, the journey reveals its final transformation. The Sun appears faint, yet still defines the gravitational structure of the environment. Neptune's blue atmosphere emerges gradually from the darkness, not as an abrupt arrival, but as a slow increase in reflected light and scientific signal strength. After years of travel, the spacecraft transitions from interplanetary traveler to local observer, entering a region where orbital insertion or flyby operations begin to define its final mission phase. The total duration to reach Neptune is therefore not simply a measure of distance divided by speed. It is the result of layered constraints involving propulsion technology, gravitational interactions, orbital alignment, and communication limits. Each of these factors contributes to the extended timeline that stretches missions across more than a decade. In this distant region, travel time itself becomes a reflection of the solar system's structure, where vast spaces between worlds define not only physical separation, but also the rhythm of exploration. The path toward Uranus extends deeper into the outer solar system, where distance begins to reshape the meaning of travel even further. Uranus orbits at roughly 2.9 billion kilometers from the Sun, and from Earth the journey depends heavily on orbital alignment and energy-saving trajectories. Spacecraft do not move directly outward in a straight line toward this distant world. Instead, they follow curved interplanetary paths shaped by gravitational forces, where the combined motion of Earth, the Sun, and other planets defines a long arc of transfer. Even when conditions are favorable, reaching Uranus typically requires around 8 to 15 years of travel time, depending on the trajectory and propulsion strategy chosen at launch. This duration reflects the challenge of moving deeper into a region where the Sun's influence still governs motion, but with significantly reduced strength compared to the inner solar system. Spacecraft departing from Earth first build heliocentric velocity, entering an orbit around the Sun that is slightly larger or smaller, depending on whether they are heading inward or outward. For Uranus-bound missions, this orbit expands gradually through carefully timed engine burns and gravitational assists. Jupiter often plays a central role in shaping the trajectory, providing a powerful gravitational boost that redirects spacecraft toward the distant outer planets. Without such assistance, travel times would increase dramatically, requiring far more fuel than current systems can support. As the spacecraft moves farther from the Sun, the environment becomes progressively quieter in both physical and energetic terms. Solar radiation weakens to a fraction of its intensity at Earth, and sunlight itself becomes a faint cold illumination rather than a strong energy source. This shift affects onboard systems, particularly those that rely on solar panels. At Uranus distance, many missions depend on nuclear power sources because sunlight is too weak to sustain continuous operations. This technological adaptation allows instruments to function steadily across the long journey and during arrival in the distant planetary system. The journey toward Uranus is also defined by long periods of steady, nearly unchanging motion. After major trajectory corrections and gravity assists are completed, spacecraft often spend years coasting along predetermined paths. During this time, there are few dramatic course changes. Instead, navigation becomes a process of precise measurement and small adjustments. Even minor velocity changes early in the mission can accumulate over millions of kilometers, determining whether a spacecraft arrives at the correct position years later. This sensitivity to initial conditions highlights the delicate structure of interplanetary travel, where small decisions made near Earth influence outcomes across vast spans of time and space. Communication delay becomes more pronounced as distance increases. Signals traveling between Earth and a spacecraft near Uranus can take more than 2 hours one way. This delay transforms mission control into a system of anticipation and prediction. Commands are prepared long in advance, and spacecraft systems are designed to handle unexpected conditions without immediate human intervention. As distance increases, autonomy becomes essential. Instruments must adjust to changing environments, manage power levels, and continue scientific observations without waiting for real-time instructions from Earth. The region between Saturn and Uranus is not empty. It contains sparse dust, solar wind particles, and remnants of early solar system formation. Although extremely thin, this medium still represents the extended influence of the Sun, which gradually weakens but never fully disappears. Spacecraft passing through this region experience a transition in which solar wind pressure becomes minimal and the heliosphere begins to feel more diffuse. These subtle changes do not alter trajectory in a dramatic way, but they contribute to the broader scientific understanding of how the solar system interacts with interstellar space. Uranus itself presents a unique arrival environment. Its atmosphere is composed primarily of hydrogen, helium, and methane, with methane absorbing red light and giving the planet its distinct blue-green appearance. Unlike closer planets, Uranus receives so little sunlight that its atmospheric dynamics are driven more by internal heat and complex chemical interactions than by solar energy. When a spacecraft finally approaches this region, after years of travel, the transition from interplanetary space to planetary system is gradual. The planet does not appear suddenly, but grows from a faint disk into a structured world with visible atmospheric layers and faint ring systems. Orbital mechanics around Uranus require careful planning because the planet rotates on a highly tilted axis, nearly parallel to the plane of its orbit. This unusual orientation affects both its seasons and the approach paths available for spacecraft. Arriving missions must account for the geometry of this tilt, which influences entry angles, flyby trajectories, and potential orbital insertion strategies. The complexity of this environment reflects how each planetary system presents its own navigational challenges even within the same solar system. Time perception during a Uranus mission becomes increasingly abstract. From Earth's perspective, nearly a decade may pass between launch and arrival. From the spacecraft's perspective, however, the journey consists of continuous adjustments, measurements, and slow drift through the solar system's outer region. the Sun gradually shrinks to a distant bright point, while background stars remain constant references against which motion is measured. There are no sudden changes in scenery, only the gradual shift of scale and brightness as distance accumulates. By the time Uranus is reached, the spacecraft has travelled through a significant portion of the solar system's radial structure. It has crossed the inner planetary region, passed through asteroid and gas giant zones, and entered a domain where the Sun's influence is weakened but still present. Arrival is not an abrupt event, but a transition into a new gravitational environment. The spacecraft's speed relative to Uranus must be carefully managed, as too much velocity results in a flyby, while precise adjustments can allow orbital capture. The total travel time to Uranus reflects not only distance, but also the architecture of interplanetary motion. Gravity-assist propulsion limits and orbital alignment all combine to shape journeys that extend across many years. Each mission becomes a long-term process rather than a short expedition, where planning, execution, and arrival are separated by vast intervals of time. Uranus marks a deeper threshold in solar system exploration, where travel begins to feel less like movement across space and more like a gradual unfolding of distance itself. The region of Saturn sits closer to the middle of the outer solar system, yet it already represents a dramatic expansion of travel time compared to the inner planets. Saturn orbits at roughly 1.4 billion kilometers from the Sun, and spacecraft traveling from Earth must follow carefully shaped trajectories that stretch across years. Depending on launch windows and chosen flight paths, missions to Saturn typically require about 6 to 7 years, although some indirect routes extend this duration further. The journey is not a straight crossing of space, but a long gravitational curve that reflects the structure of solar orbit dynamics. Spacecraft departing towards Saturn begin by entering an initial heliocentric orbit shaped by Earth's own motion. From there, propulsion burns adjust velocity slightly, but the most significant changes in trajectory often come from gravitational assists. Jupiter frequently plays a central role in this process, providing a strong gravitational swing that redirects spacecraft outward towards Saturn. This interaction allows missions to conserve fuel while gaining speed, but it also introduces complexity in timing, since alignment between Earth, Jupiter and Saturn must occur within precise windows that open only periodically. As a spacecraft moves beyond the asteroid belt and into the outer planetary region, the environment becomes increasingly dominated by cold, low-density space. The Sun's brightness fades further, and solar energy becomes weaker, requiring more reliance on long-duration power systems. Spacecraft designed for Saturn missions often carry nuclear power sources because solar panels at this distance generate significantly less energy than in the inner solar system. This shift in energy strategy marks an important transition in how missions are sustained over long periods. Travel towards Saturn involves long phases of steady motion after initial acceleration events. Once major trajectory corrections are complete, spacecraft often coast for years along paths that are stable but not static. These trajectories are defined by the balance between the Sun's gravity and the spacecraft's velocity, producing smooth arcs that extend across millions of kilometers. During this time, navigation teams on Earth track the spacecraft's position, using radio signals and deep space antennas, but the information received is always delayed by tens of minutes due to the increasing distance. Communication delay becomes a defining characteristic of Saturn-bound missions. Signals traveling at the speed of light require more than an hour to make a round trip between Earth and a spacecraft near Saturn. This delay forces mission operations to rely heavily on pre-programmed instructions and autonomous spacecraft behavior. Adjustments to instruments, course corrections, and scientific observations are often executed without immediate human oversight. The spacecraft becomes increasingly self-sufficient as distance grows, responding to conditions based on onboard systems rather than real-time commands. The region between Jupiter and Saturn is a transitional zone where solar radiation continues to weaken, and particle density becomes extremely low. The solar wind, a stream of charged particles flowing outward from the Sun, still extends through this region, but with reduced intensity. Spacecraft passing through it experience a quieter environment with fewer energetic disturbances than in the inner solar system. However, even this faint medium plays a role in shaping the heliosphere, the vast bubble of solar influence that encloses the planets. Saturn itself gradually emerges from the darkness as a spacecraft approaches. Its rings, composed of ice particles and rocky debris, reflect sunlight in a complex pattern that reveals structure and motion. These rings are not solid bands, but vast collections of orbiting particles, each following its own path around the planet. The visual transition from deep space to Saturn's environment is slow and layered, as the planet grows from a distant point of light into a structured system with moon's rings and atmospheric bands. Orbital arrival at Saturn requires careful control of velocity. A spacecraft arriving too quickly will pass through the system on a flyby trajectory, while a carefully timed deceleration allows for orbital insertion. This process often involves engine burns, positioned precisely to counter the spacecraft's incoming speed relative to Saturn's gravitational field. The balance between speed and gravity determines whether a mission becomes a brief encounter or a long-term exploration of the Saturnian system. Timescales become particularly striking when considering Saturn missions. From launch to arrival, nearly a decade may pass in some cases, yet the spacecraft itself experiences this period as continuous motion through space. There are no pauses or transitions in perception, only gradual changes in position and environment. The Sun slowly diminishes in brightness, while Saturn's reflected light increases until it becomes the dominant feature in the spacecraft's field of view. Saturn's moons introduce additional layers of complexity to mission planning. Titan Enceladus and other satellites move in stable orbits that must be carefully considered when designing trajectories. Each moon presents potential scientific targets, but also gravitational influences that can alter spacecraft paths. Navigating this system requires precise calculation of orbital mechanics, where even small variations in timing can lead to significant differences in final position. The total travel time to Saturn reflects the combined effects of distance propulsion limits and orbital mechanics. It is not simply a measure of how far Saturn lies from Earth, but a representation of how motion unfolds within the solar system's gravitational structure. Each mission becomes a long process of alignment, acceleration, coasting, and arrival shaped by both human planning and planetary motion. Saturn thus stands as a midpoint in interplanetary travel, where journeys are already long but still connected to the inner solar system in terms of communication and control. By the time a spacecraft reaches Saturn, it has already spent years crossing structured regions of space, transitioning from inner planetary orbits to the deep outer system. The experience of travel is defined less by change in scenery and more by the gradual accumulation of distance and time. Saturn marks a threshold where exploration begins to extend beyond familiar timescales, entering missions that require patience measured in nearly a decade. The region of Jupiter marks a major turning point in interplanetary travel, not only because of its scale, but because of its gravitational influence on nearly every mission that passes through the outer solar system. Jupiter orbits at roughly 780 million kilometers from the Sun, and spacecraft traveling from Earth can reach it in about 13 months to several years depending on trajectory design. Fast transfer paths often supported by gravity assists, and optimized launch windows can shorten the journey to just over a year. While more complex scientific missions that require specific arrival conditions may extend travel time closer to 2 or more years, the journey toward Jupiter begins with a controlled departure from Earth's orbit, where the spacecraft must first match the general direction of the solar system's rotation around the Sun. Once in heliocentric orbit, the spacecraft begins a carefully planned spiral outward. The most important acceleration often comes from Earth itself or Venus in earlier flybys, followed by Jupiter's own powerful gravitational field, which can dramatically alter the spacecraft's speed and direction. This gravitational assist is one of the most efficient tools in interplanetary navigation, allowing spacecraft to gain energy without using additional fuel. As the spacecraft moves deeper into the outer solar system, the Sun's intensity decreases, but still provides enough energy for some missions to rely on solar panels, although at Jupiter's distance this becomes increasingly challenging. Many spacecraft instead rely on nuclear power systems to maintain consistent energy output. This ensures that instruments remain active even in the cold, dim environment, where sunlight is only a fraction of what reaches Earth. Travel time to Jupiter is relatively short compared to the outer planets, yet it still involves long periods of continuous motion. After initial trajectory burns and gravity-assist spacecraft often coast for months or years, with only occasional course corrections. These corrections are extremely small but essential, as they ensure that the spacecraft intersects Jupiter's vast gravitational field at the correct angle and speed. Even a slight deviation early in the journey can lead to significant changes in arrival conditions. Communication with a spacecraft near Jupiter experiences noticeable delay, though still manageable compared to more distant regions. Signals may take tens of minutes to travel between Earth and the spacecraft. This delay requires mission teams to rely on predictive control systems and autonomous spacecraft operations. Instruments must often adjust exposure levels, pointing directions, and data collection modes without waiting for immediate instructions from Earth. Jupiter's gravitational field dominates the surrounding region of space. As a spacecraft approaches, the planet's influence begins to shape its trajectory more strongly than the Sun's in relative terms. This transition is gradual but significant, marking the point where local planetary gravity becomes the primary factor in navigation. The spacecraft's path bends sharply as it enters this region, often resulting in flybys of Jupiter's moons or direct entry into orbital capture trajectories. The visual transition toward Jupiter is one of the most dramatic in the solar system. From a distant point of light, the planet slowly expands until its cloud bands become distinguishable. These bands are driven by powerful atmospheric dynamics, where hydrogen and helium gases move in alternating belts of high-speed winds. The Great Red Spot, a massive storm system larger than Earth, becomes visible as a persistent swirling feature in the atmosphere. This gradual emergence reflects not only proximity, but also the increasing resolution of scientific instruments as distance closes. Jupiter's moons play a crucial role in mission planning and scientific exploration. The Galilean moons, including Io, Europa, Ganymede, and Callisto, each present unique environments shaped by gravitational interactions with the planet. Spacecraft often use flybys of these moons to adjust trajectory and gain additional scientific data. These interactions can extend mission timelines slightly, but also provide valuable opportunities to refine orbital paths or collect detailed observations. The travel time to Jupiter is also shaped by the timing of launch windows. Because Earth and Jupiter move at different speeds around the Sun, optimal transfer opportunities occur at intervals that allow efficient orbital alignment. These windows determine whether a mission can take a fast direct transfer, or must follow a longer, more energy-efficient path. As a result, planning for Jupiter missions often begins years before launch, with trajectory design tightly constrained by celestial mechanics. Once a spacecraft arrives in the Jovian system, the journey transitions from interplanetary travel to localized exploration. The spacecraft may enter orbit around Jupiter or one of its moons, or perform a series of flybys that gradually shift its path through the system. This phase marks a shift in mission focus from transit to observation, where the long journey time gives way to sustained scientific study. The total duration to reach Jupiter reflects both distance and the efficiency of modern trajectory design. While it is one of the faster interplanetary journeys to the outer solar system, it still represents a significant portion of a mission's lifetime. The spacecraft experiences this time as a continuous progression through space with gradual changes in solar brightness and increasing dominance of Jupiter's gravitational presence. Jupiter thus stands as a gateway to deeper space exploration. Missions that pass this point often continue towards Saturn, or beyond, using Jupiter as a gravitational stepping stone. The time required to reach it defines the beginning of a long-duration exploration beyond the inner solar system, where travel is no longer measured in months alone but in extended phases of carefully structured motion through increasingly distant regions of space. The asteroid belt occupies a wide region between the inner rocky planets and the outer gas giants, stretching roughly between Mars and Jupiter at distances of about 250 million to 400 million kilometers from the Sun. Although often imagined as a dense field of rocks, it is in reality a vast and sparsely populated zone, where individual objects are separated by enormous distances. For spacecraft traveling through this region, the asteroid belt does not significantly increase travel time in a direct mechanical sense, but it represents an important phase in interplanetary journeys where navigation continues under stable solar gravity, while environmental conditions shift toward colder, darker space. Spacecraft typically cross the asteroid belt during missions to the outer planets, especially Jupiter and beyond. The time spent traversing this region is relatively short compared to the overall journey, often measured in weeks or months depending on trajectory speed. However, the belt still plays a role in mission planning because it lies along the natural path shaped by orbital mechanics. Spacecraft do not slow down significantly when passing through it. Instead, they continue along long elliptical or hyperbolic trajectories established earlier in the mission. The perception of time in this region is shaped by continuity rather than change. Once a spacecraft leaves the inner solar system, it enters a long phase of steady motion, where the influence of Earth becomes minimal. The asteroid belt is not a barrier but a transitional band within this larger flow outward. The Sun remains the central gravitational anchor, and spacecraft continue to orbit it even as they move farther away. This orbital motion defines travel time more than any physical obstacle. Navigation through the asteroid belt requires attention but not avoidance of dense hazards. The distances between asteroids are so large that direct collisions are extremely unlikely. Instead, spacecraft focus on maintaining precise trajectories, ensuring that their long-term path remains aligned with mission goals. Small adjustments made earlier in the journey determine whether the spacecraft passes through the belt on a stable course toward outer planets or drifts into less optimal orbital geometry. As distance increases, solar energy continues to weaken, though not yet to the extreme levels found in the outer planetary regions. Spacecraft operating in this zone still receive enough sunlight for many instruments to function effectively, though power management becomes increasingly important. Thermal control systems ensure that instruments remain within operational temperature ranges as the environment cools steadily with distance from the Sun. Communication delay in the asteroid belt remains relatively small compared to outer solar system missions. Signals still travel in minutes rather than hours, allowing mission teams to maintain near-continuous contact. However, even this moderate delay reinforces the importance of autonomy in spacecraft operations. Systems must handle short-term adjustments independently while awaiting confirmation from Earth. The asteroid belt also represents a region of scientific interest rather than a true obstacle. It contains remnants from the early solar system material that never coalesced into a planet due to Jupiter's strong gravitational influence. These fragments provide insight into the formation of planetary systems, and spacecraft passing through may collect data on dust density, particle composition, and magnetic conditions. The travel time through this region is therefore not only a transit phase but also an opportunity for observation. From a dynamical perspective, the asteroid belt is part of a continuous gradient of orbital motion rather than a discrete zone. Objects within it follow stable orbits around the Sun shaped by gravitational interactions over billions of years. Spacecraft passing through share this same fundamental motion, differing only in trajectory, shape, and speed. The experience of travel is defined less by interaction with the belt itself, and more by the gradual expansion of orbital scale. The transition beyond the asteroid belt marks a psychological and operational shift in mission design. Spacecraft moving outward begin to enter regions where solar influence continues to weaken, and travel times to destinations increase significantly. Even though the belt itself does not impose a major delay, it symbolizes the boundary between familiar planetary space and the more extended outer solar system. Trajectory design for missions crossing this region remains tightly controlled. Engineers ensure that spacecraft paths remain smooth and efficient, avoiding unnecessary course changes that would consume fuel or extend mission duration. Once past the belt, spacecraft often enter long coasting phases that define the majority of interplanetary travel time to outer planets. The asteroid belt therefore represents a brief but important passage in the broader timeline of planetary exploration. It is not a destination that extends travel time in a significant way, but rather a structured environment through which spacecraft pass on their way to more distant worlds. Its role is defined by continuity stability and the gradual transition from inner to outer solar system dynamics. As spacecraft exit the belt region, they continue into deeper space where planetary encounters become less frequent and distances expand dramatically. The journey time to any destination beyond this point is shaped increasingly by gravitational assists, orbital alignment, and the weakening influence of the Sun. The asteroid belt thus serves as a midpoint marker in interplanetary travel, not by slowing missions, but by situating them within the broader flow of solar system structure. Mars represents the most accessible planet beyond Earth, yet even this closest interplanetary neighbour requires travel times measured in months rather than days. Depending on orbital alignment and propulsion strategy, missions to Mars typically take about 6 to 9 months using current technology, although variations can extend this range. The journey begins only during specific launch windows that occur roughly every 26 months, when Earth and Mars are positioned in favourable alignment around the Sun. These windows define the geometry of interplanetary travel, ensuring that spacecraft can follow efficient transfer orbits rather than expending excessive energy. A spacecraft departing toward Mars enters a heliocentric transfer orbit shaped by the balance between Earth's orbital velocity and the Sun's gravity. This trajectory is often an elongated ellipse that gradually carries the spacecraft outward from Earth's orbit to meet Mars at the correct point in its path. The timing of departure is critical because both planets continue moving throughout the journey. Mars is not a stationary destination, but a moving target requiring precise prediction of its future position months in advance. During the cruise phase, the spacecraft experiences long periods of steady motion with only occasional course corrections. These corrections are small but necessary to refine the trajectory and ensure accurate arrival conditions. Without them, even minor deviations could result in missing Mars by thousands of kilometers. The spacecraft coasts through space in a quiet, stable path governed primarily by the Sun's gravity, which remains the dominant force throughout the inner solar system. Communication between Earth and a Mars-bound spacecraft becomes increasingly delayed as distance grows. At closest approach, signals may take only a few minutes to travel one way, but at greater distances this delay can extend to over 20 minutes. This growing lag fundamentally changes mission operations. Instead of direct control, engineers rely on pre-programmed sequences and autonomous systems that allow the spacecraft to respond to conditions without immediate human input. The environment between Earth and Mars is relatively structured compared to deeper space regions. Solar radiation remains strong enough to power instruments using solar panels, making Mars missions less dependent on nuclear energy compared to outer solar system exploration. However, thermal variations still require careful management as spacecraft pass through regions of increasing and decreasing solar intensity, depending on orbital position. The Mars transfer trajectory is often described as energy efficient but time constrained. Faster routes require significantly more propulsion, while slower routes conserve fuel but extend travel time. Most missions balance these factors by selecting a mid-range trajectory that minimizes fuel use while keeping travel duration within practical limits. This balance defines the standard 6 to 9 month journey time that has become typical for Mars exploration. As the spacecraft approaches Mars, the planet gradually grows from a small reddish point of light into a visible disk. Surface features such as dust storms and polar ice caps begin to emerge through increasingly detailed imaging. This transition is not sudden, but gradual, reflecting the steady closing of distance rather than abrupt arrival. The spacecraft continues to move at high relative speed, requiring careful navigation to ensure proper orbital insertion or landing trajectory. Mars arrival is one of the most complex phases of interplanetary travel. The spacecraft must either slow down enough to be captured into orbit or descend through the atmosphere for landing. Both processes require precise timing and controlled use of propulsion systems. The thin Martian atmosphere adds complexity as it is thick enough to generate heat during entry, but too thin to provide strong aerodynamic braking without additional systems. The total travel time to Mars reflects not only distance, but also orbital mechanics and energy constraints. Although it is the shortest planetary journey beyond Earth, it still requires sustained operation over many months. During this time, the spacecraft moves through a continuous arc of motion around the Sun, gradually transitioning from Earth's orbital path to Mars's orbital region. Mars serves as a reference point for human interplanetary exploration because of its relative proximity and manageable travel time. Yet even this shortest journey highlights the scale of the solar system, where reaching another planet requires months of continuous travel through space. The spacecraft experiences this journey as an unbroken progression of motion, with no stops or interruptions, only gradual changes in position and environment. Upon arrival, Mars becomes both destination and new operational environment. The spacecraft transitions from interplanetary travel to orbital insertion, or surface operations, marking the end of the transfer phase. The months spent in transit are defined by steady motion, careful navigation, and increasing communication delay, all of which shape the experience of reaching another world. Mars thus represents the first major threshold in interplanetary travel time. It is close enough to reach within a single human calendar year, yet distant enough to require precise planning and sustained operation. The journey establishes the baseline for understanding all further travel in the solar system, where distances increase and timescales expand dramatically. Venus sits closer to Earth than Mars in terms of orbital distance, yet travel time to Venus is not always shorter or simpler. Depending on orbital alignment and chosen trajectory, spacecraft journeys to Venus typically take about 3 to 5 months. This duration is shaped by the same orbital mechanics that govern all interplanetary travel, where planets are constantly moving, and spacecraft must follow carefully timed transfer paths rather than direct straight-line routes. A mission to Venus begins with launch into a heliocentric transfer orbit that bends inward toward the Sun. Unlike missions heading outward, Venus-bound spacecraft must lose orbital energy relative to Earth's position around the Sun. This is achieved through carefully calculated propulsion burns and gravitational assists, sometimes involving Earth or Venus itself on previous flybys. The result is a controlled inward spiral that brings the spacecraft closer to the Sun while aligning it with Venus's future position. The timing of Venus missions is governed by synodic cycles between Earth and Venus, which occur more frequently than Mars launch windows. These cycles determine when the two planets are positioned in a way that allows efficient transfer orbits. Even though Venus is closer, the relative motion of both planets still requires precise planning, and missing a launch window can significantly extend travel time. During the cruise phase, the spacecraft moves steadily inward toward the Sun, experiencing increasing solar radiation. Unlike outer planet missions where sunlight weakens, Venus missions encounter intensifying heat and energy conditions. This requires careful thermal design, as spacecraft systems must remain stable under higher solar exposure. Instruments and electronics are shielded and regulated to prevent overheating as distance decreases. Communication delays remain relatively short compared to outer solar system missions. Signals between Earth and a Venus-bound spacecraft typically take only a few minutes one way, depending on distance. This allows for more responsive mission control compared to deep space exploration, although autonomous systems are still essential during critical maneuvers, such as orbital insertion or atmospheric entry. The interplanetary medium between Earth and Venus is similar to other inner solar system regions dominated by the solar wind and sparse particle distributions. As the spacecraft moves inward, solar radiation pressure becomes more noticeable, subtly influencing trajectory over long durations. Navigation systems account for these effects, ensuring that small perturbations do not accumulate into significant deviations. Venus itself presents a rapidly changing visual target during approach. Initially appearing as a bright point of light, it gradually expands into a crescent shape as the spacecraft closes distance. The planet's thick atmosphere, composed primarily of carbon dioxide with dense cloud layers, reflects sunlight, strongly making Venus one of the brightest objects in the sky when viewed from Earth or nearby space. Unlike Mars, Venus arrival does not always involve surface landing missions because its extreme surface conditions present significant engineering challenges. Many missions focus on orbital insertion or atmospheric entry probes designed to survive only short periods within the dense high-pressure atmosphere. As a result, travel time to Venus is often followed by relatively brief operational phases for surface contact instruments. The inward journey toward Venus also represents a gradual increase in solar gravitational influence. As the spacecraft approaches closer to the Sun than Earth's orbit, orbital velocities increase and trajectory adjustments become more sensitive. Small navigational errors can have larger effects due to stronger gravitational gradients, requiring precise control during final approach. Despite being closer than Mars, Venus missions are not always faster in every aspect of mission design. Launch constraints, orbital alignment, and mission objectives can sometimes result in similar or even longer preparation times compared to Mars missions. However, Once launched, the physical travel duration remains shorter due to reduced heliocentric distance. Venus therefore represents a unique case in interplanetary travel time. It is both nearby and dynamically complex, requiring careful synchronization of orbital mechanics and thermal engineering. The journey highlights how proximity alone does not define travel duration in space. Instead, the continuous motion of planets and the structure of solar orbits determine the true length of interplanetary journeys. As the spacecraft nears Venus, the Sun grows brighter and more intense in the background, while the planet itself becomes a dominant presence in the field of view. The transition from Earth to Venus is marked not by sudden change, but by steady inward motion through increasingly energetic space. Arrival completes a journey defined by contraction rather than expansion, moving closer to the Sun rather than outward into darkness. Venus thus stands as a reminder that interplanetary travel time is shaped by orbital dynamics rather than simple distance. Even the closest planetary neighbors require months of sustained motion through a continuously shifting gravitational environment. Mercury lies closest to the Sun, yet reaching it is one of the most complex journeys in the solar system. Travel time to Mercury typically ranges from about 6 months to more than 7 years, depending on mission design, trajectory choice, and the number of gravitational assists used. Although the planet is physically closer to Earth than the outer planets, the difficulty of shedding orbital energy toward the Sun makes direct travel inefficient. Spacecraft must lose a large portion of their angular momentum around the Sun, which requires long, carefully structured paths rather than direct inward motion. A mission toward Mercury begins in Earth's orbit, where the spacecraft first establishes a heliocentric trajectory. Instead of simply falling inward toward the Sun, the spacecraft often travels outward first, or performs multiple planetary flybys to gradually reduce its orbital energy. Venus and Earth are commonly used as gravitational assist partners, allowing the spacecraft to adjust its path without excessive fuel consumption. These repeated encounters with inner planets stretch the total mission timeline significantly, even though the final destination is the closest planet to the Sun. The inner solar system is dominated by increasingly strong solar gravity, and this creates a paradox in travel time. Moving closer to the Sun does not necessarily mean faster arrival. Instead, spacecraft must carefully manage orbital velocity, ensuring they slow down relative to the Sun, while still maintaining enough momentum to follow stable transfer paths. This balancing act often requires multiple years of looping trajectories before the spacecraft is finally positioned to approach Mercury. During the cruise phase, the spacecraft experiences rapidly increasing solar intensity. As distance to the Sun decreases, radiation levels rise sharply, and thermal control becomes one of the most critical engineering challenges. Spacecraft approaching Mercury must withstand extreme heating conditions, especially during close solar passes. Specialized heat shields and reflective materials are used to protect instruments from intense sunlight that can be several times stronger than what is experienced near Earth. Communication with a Mercury-bound spacecraft remains relatively fast compared to outer solar system missions, with signal delays measured in minutes. However, the environment introduces other operational challenges. Solar radiation can interfere with onboard electronics and instruments, requiring shielding and robust system design. The spacecraft must operate reliably in conditions where both heat and radiation are significantly higher than in most other planetary missions. Trajectory design for Mercury missions often includes long periods of orbital adjustment. Instead of a single direct transfer, spacecraft may complete multiple revolutions around the Sun, gradually lowering their perihelion with each pass. Each loop brings the spacecraft closer to Mercury's orbital path, reducing relative velocity until orbital insertion becomes possible. This process is highly time-consuming but essential for achieving stable arrival. Mercury itself orbits the Sun in a highly elliptical path and moves quickly compared to other planets. This means that spacecraft must not only reach the correct distance, but also match orbital speed and timing. Arrival is therefore a complex synchronization of position and velocity, where even small mismatches can prevent capture into orbit. The Sun's gravitational influence dominates this region, making precise calculations essential for successful mission completion. Unlike outer planets, Mercury does not have a significant atmosphere to assist in orbital insertion. This removes the possibility of aerodynamic braking, forcing spacecraft to rely entirely on propulsion maneuvers to slow down. These braking burns are energy-intensive and must be carefully timed to ensure the spacecraft is captured into orbit, rather than passing by the planet. The total travel time to Mercury reflects this combination of orbital difficulty and thermal challenge. Although it is the closest planet to the Sun, it often requires longer mission durations than more distant worlds because of the complexity of reducing solar orbital energy. Each mission becomes a slow inward spiral through increasingly intense solar conditions, where time is extended by repeated adjustments rather than direct motion. As the spacecraft approaches Mercury, the Sun dominates the sky with overwhelming brightness. The planet appears as a small, heavily cratered world moving rapidly across the field of view. The transition from interplanetary space to Mercury's environment is marked by intense lighting contrast and rapid orbital dynamics. The spacecraft must execute final maneuvers precisely to match Mercury's fast orbital motion. Mercury thus demonstrates that proximity does not simplify travel in the solar system. Instead, the structure of orbital mechanics defines journey duration more strongly than distance alone. Reaching the closest planet to the Sun requires some of the longest and most intricate paths, where time is shaped by the need to continuously reduce orbital energy rather than simply move inward. The journey concludes with the spacecraft either entering orbit or performing a flyby, marking the end of a long inward spiral through the most energy-demanding region of the solar system. Mercury stands as a reminder that in space travel direction and velocity matter as much as distance, and that the shortest physical gap can still demand the longest time to cross. Earth serves as the baseline reference for all interplanetary travel time, not because it is the center of the solar system, but because it is the starting point from which all missions are measured. Every journey outward begins with Earth's orbital motion around the Sun, and this motion immediately shapes the structure of transfer trajectories. Spacecraft do not depart into static space. They leave a planet already moving at high speed along its orbit, and this velocity becomes part of the initial conditions that define every subsequent path. The concept of Earth as a reference orbit means that travel time is always relative to changing geometry. Earth and other planets continuously shift positions around the Sun, so distance between worlds is never fixed. A spacecraft launching from Earth begins its journey in a moving frame of reference, and the timing of departure determines the entire structure of the trajectory. Even small differences in launch timing can produce large variations in arrival time, because planetary alignment controls how efficiently orbital energy can be transferred. Earth's gravitational influence also plays a role at the beginning of every mission. Spacecraft must first escape the planet's gravity well, which requires a specific amount of energy to reach heliocentric orbit. This initial phase contributes to total mission duration, although it is short compared to interplanetary cruise times. Once the spacecraft escapes Earth's immediate gravitational field, it transitions into an orbit around the Sun where long-duration travel begins. From Earth's perspective, interplanetary travel time appears as a sequence of launch windows separated by months or years. These windows are defined by orbital mechanics where planets align in positions that allow efficient transfer paths. Between these windows, missions must wait sometimes for long periods before launch becomes energetically favourable. This waiting period is an invisible but essential part of total travel time when considering full mission planning from Earth. Communication systems anchored on Earth define another aspect of Earth's role as a reference point. All signals to and from spacecraft originate and return to Earth-based antennas, creating a central hub for navigation and control. Even as spacecraft move farther away, Earth remains the fixed point of coordination. Signal delay increases with distance, but Earth continues to define mission timing, data interpretation, and operational control. The environment near Earth also shapes early mission phases. The region includes the Moon's orbit near Earth space and the early portion of heliocentric trajectory. In this zone, spacecraft are still strongly influenced by Earth's gravity and must perform precise maneuvers to ensure correct departure angle. Any errors during this stage propagate through the entire journey, affecting arrival time at distant destinations. Earth's orbit around the Sun defines the fundamental unit of interplanetary motion. One full orbit represents a year, and all planetary travel times are measured relative to this cycle. Mars transfer windows, Venus opportunities, and outer planet alignments are all synchronized with Earth's position in this orbital cycle. This makes Earth not a central object in a physical sense, but a temporal anchor for navigation and scheduling. As spacecraft leave Earth's vicinity, they enter a region where solar gravity becomes the dominant force. Yet Earth's influence remains conceptually important, because every trajectory is designed from its starting conditions. The velocity, direction, and timing of departure are all defined relative to Earth's motion, which establishes the initial framework for the entire journey. Earth-based observation systems also track spacecraft throughout their missions. Deep space networks monitor signals as they weaken with distance, providing continuous updates on position and velocity. This tracking ensures that travel time is not only measured in motion through space, but also in continuous observation from a fixed point. Earth remains the lens through which all interplanetary travel is understood. The role of Earth as a reference also highlights the relative nature of time in space exploration. A journey that lasts months to Mars or years to outer planets is always measured against Earth's calendar system. This creates a structured framework where interplanetary travel is integrated into human perception of time, even though the spacecraft itself experiences only continuous motion without pauses. Earth therefore functions as both origin and measurement standard. Every planetary travel time begins with its orbital context and ends in relation to its observational framework. Even the most distant missions remain connected to Earth through timing communication and navigation systems. Without Earth as a reference, interplanetary travel would lose its structured meaning, becoming only motion through space without defined duration. As the foundation of all mission timelines, Earth anchors the entire system of interplanetary exploration. It provides the starting point for trajectories, the timing for launch windows, and the frame of reference for all measured durations. Every travel time to every planet is ultimately a variation of how motion begins from this single orbital position around the Sun. The Sun dominates interplanetary travel not as a destination, but as the central gravitational structure that governs every trajectory within the solar system. Every spacecraft path, regardless of its target, is shaped by the Sun's mass and the curved geometry of space around it. Travel time to any planet is therefore not only a matter of distance, but also a consequence of how motion unfolds within this gravitational field. Even when spacecraft move outward toward distant worlds, or inward toward Mercury, they remain in continuous orbit around the Sun, following paths that are never truly straight. the Sun's gravity well defines the energy landscape of interplanetary travel. To move between planets, spacecraft must constantly adjust their orbital energy relative to the Sun. Increasing distance requires gaining heliocentric energy, while moving inward requires losing it. These adjustments cannot be made in a single step with current technology, so missions rely on gradual transitions through carefully designed orbits. Each change in trajectory reflects an exchange of energy between motion and gravitational influence, extending travel time into months or years depending on the destination. Solar radiation also plays a role in shaping mission design. As distance increases, sunlight weakens, affecting power generation for spacecraft systems. In the inner solar system, solar panels provide abundant energy, but farther out they become less effective, requiring alternative power sources. This gradual shift in energy availability influences not only engineering design, but also mission duration, since power constraints limit operational flexibility during long journeys. The Sun's gravitational field also ensures that all planetary motion remains interconnected. Planets do not sit still in space. They continuously orbit the Sun at different speeds and distances. This constant motion means that spacecraft must chase moving targets rather than fixed destinations. Travel time is therefore influenced not only by how far a planet is, but also by where it will be in the future. Trajectories are designed to intercept planets at precise moments when orbital alignment is achieved. Communication across the solar system remains anchored to Earth, but all signals pass through the Sun's gravitational environment. Although gravity does not slow light in a measurable way on these scales, the structure of space defined by the Sun determines the geometry of communication paths. As distance increases, signal delay grows, reinforcing the separation between spacecraft and Earth. Yet even at extreme distances, the Sun remains the central reference point for both motion and measurement. Spacecraft traveling through the solar system experience the Sun's influence continuously, even at the outermost regions. The heliosphere, a vast bubble of solar wind and magnetic influence, extends far beyond the orbit of Pluto. Within this region, particles emitted by the Sun flow outward, shaping the environment through which spacecraft travel. Although extremely thin, this medium represents the extended presence of the Sun across the entire system. Travel time between planets can be understood as different expressions of motion within this solar framework. Inner planets require short transfers due to strong gravitational gradients and frequent alignment opportunities. Outer planets require long trajectories because of greater distances and reduced energy transfer efficiency. In all cases, the Sun defines the structure within which these journeys occur, making it the underlying organizer of all interplanetary travel. The Sun also determines the boundaries of efficient navigation. Gravity assists rely on planetary encounters that themselves exist within the Sun's orbital system. Without the Sun's central mass, there would be no stable planetary orbits and no predictable transfer windows. The entire architecture of interplanetary travel depends on this single, gravitational center, which organizes both motion and time across the system. As spacecraft move farther from or closer to the Sun, their velocities adjust according to orbital mechanics. These changes are not constant accelerations, but continuous adaptations to curved space. This results in long, smooth trajectories that define the true nature of travel time. Motion is not a straight line, but a persistent fall around the Sun shaped by balance between velocity and gravity. Ultimately, the Sun defines both the structure and the rhythm of interplanetary journeys. Every mission begins within its gravitational field, moves through paths shaped by its influence, and remains bound to it even at the farthest edges of exploration. Travel time to every planet is therefore a reflection of how motion unfolds around this central star, where distance, velocity, and alignment are all expressions of the same underlying system. The The solar system is not a collection of isolated destinations, but a single interconnected gravitational environment. Within it, the Sun acts as the anchor for all movement, ensuring that every journey, regardless of direction, follows the same fundamental rules of orbital motion. Interplanetary travel time is ultimately a measure of how spacecraft navigate this continuous solar structure, moving through space that is always shaped by the presence of the star at its center. Transfer windows define the hidden rhythm behind all interplanetary travel shaping, when missions can leave Earth and how long they take to reach their destinations. These windows occur because planets move continuously along their orbits, and efficient travel requires alignment between departure and arrival positions. Without this alignment, spacecraft would need significantly more energy, or much longer flight paths. As a result, interplanetary journeys are not available at any moment in time, but instead open and close according to orbital cycles that repeat over months or years. For Mars missions, these cycles occur approximately every 26 months when Earth and Mars reach a configuration that allows a minimum energy transfer path. During these periods, spacecraft can follow an elliptical orbit that intersects Mars's future position in space. Outside these windows, missions become less efficient and require either longer travel times or impractical amounts of fuel. This constraint makes launch timing one of the most critical factors in determining total mission duration. Venus transfer windows occur more frequently due to its closer orbit and faster orbital period around the Sun. These opportunities arise roughly every 19 months, allowing more frequent missions but still requiring precise timing. Even though Venus is nearer in distance than Mars, the same orbital principles apply. The spacecraft must still intercept a moving target along a curved solar orbit, making timing essential to minimizing travel time. Outer-planet missions, such as those to Jupiter, Saturn, Uranus, and Neptune, depend on more complex alignment conditions. These missions often rely on rare configurations involving multiple planets to enable gravity assist that reduce travel time. In some cases, a single launch window may be optimal only once every several years, or even decades depending on mission design. This rarity contributes to the long planning cycles required for deep space exploration. Transfer windows also reflect the geometry of heliocentric orbits. Each planet moves at a different speed depending on its distance from the Sun. Inner planets complete orbits quickly, while outer planets move more slowly. This difference creates constantly shifting angles between planets, meaning that the most efficient travel paths are always temporary. Spacecraft must depart within these narrow periods to take advantage of favorable alignment. The concept of a transfer window also influences how spacecraft are designed. Engineers must account for not only the destination, but also the timing of arrival. A spacecraft launched during one window will arrive at a different moment in the destination planet's orbit than one launched months earlier or later. This sensitivity requires precise prediction of planetary motion years into the future. During waiting periods between transfer windows, missions remain on Earth in preparation. Spacecraft are assembled, tested, and stored until orbital geometry becomes favorable. These waiting periods are part of total mission time in a broader sense, even though they occur before launch. Interplanetary travel is therefore not only the time spent in space, but also the time spent waiting for the correct configuration of the solar system. Once a transfer window opens, launch opportunities are often limited to a narrow time frame of days or weeks. Missing this period can delay a mission for months or years. This constraint emphasizes the importance of synchronization between engineering readiness and celestial mechanics. The solar system itself dictates when travel can begin. Transfer windows also determine the shape of trajectories. Faster transfers require more energy and result in shorter travel times, but higher fuel consumption. Slower transfers conserve energy, but extend the journey significantly. Engineers choose between these options depending on mission priorities, balancing time cost and scientific objectives. The existence of transfer windows reveals that interplanetary travel is governed more by timing than by distance alone. Even planets that are relatively close may require long waits before travel becomes possible. Conversely, distant planets can sometimes be reached efficiently when alignment is favorable. Time in space exploration is therefore structured around cycles rather than continuous availability. These orbital cycles repeat predictably, forming a long-term rhythm that shapes exploration strategy. Mission planners rely on decades of astronomical data to forecast when optimal conditions will occur. This predictive structure allows humanity to schedule journeys across the solar system with remarkable precision, despite the immense distances involved. In essence, transfer windows transform the solar system into a dynamic scheduling system, where planets continuously move through positions that open and close pathways between worlds. Travel time is not only measured in months or years of flight, but also in the waiting periods that precede departure. The full duration of reaching any planet includes both motion through space and alignment within this ever-shifting orbital framework. Gravity assists are one of the most important mechanisms that shape interplanetary travel time, allowing spacecraft to gain or lose orbital energy without using large amounts of fuel. These maneuvers rely on the gravitational field of a planet to alter a spacecraft's trajectory as it passes nearby. The effect does not come from a simple pull, but from the exchange of momentum between the spacecraft and the moving planet as both travel around the Sun. This interaction can significantly shorten travel time to distant destinations or make otherwise impossible missions feasible. A gravity assist begins when a spacecraft approaches a planet on a carefully calculated path. As it falls into the planet's gravitational influence, it accelerates, gaining speed relative to the planet. As it swings around and exits the encounter, its direction changes and its velocity relative to the Sun is altered. The key feature of this process is that the spacecraft effectively borrows a small amount of orbital energy from the planet's motion around the Sun. Although the planet's change is negligible due to its large mass, the spacecraft can gain a substantial boost. Jupiter is the most powerful source of gravity assists in the solar system due to its massive size. Many missions to the outer planets depend on Jupiter flybys to reach destinations like Saturn, Uranus, or Neptune within practical timeframes. Without Jupiter's assistance, travel times to these distant worlds would increase dramatically, often beyond the limits of current mission design. The timing of these encounters is extremely precise, requiring alignment between Earth, Jupiter, and the target planet. Inner planet missions also use gravity assists, but in a different way. Spacecraft heading toward Venus or Mercury often use repeated flybys of Earth or Venus to gradually reduce their orbital energy. Instead of speeding up, these assists help slow the spacecraft relative to the Sun, allowing it to spiral inward. This process can extend mission duration, but it is necessary to reach regions close to the Sun without excessive fuel consumption. Gravity assists do not act instantly, but unfold over hours or days as the spacecraft passes through a planet's gravitational field. The exact trajectory must be planned with extreme precision, as small errors can result in significant changes to the final path. These maneuvers are among the most carefully calculated events in space navigation, often determined years before launch. The effect of a gravity assist depends on the relative motion between the spacecraft and the planet. If the spacecraft approaches from behind a planet's orbit, it can gain speed as the planet pulls it forward. If it approaches from the opposite direction, it can lose energy and slow down. This flexibility allows mission designers to shape trajectories in complex ways, effectively using planets as natural propulsion systems. Travel time reductions achieved through gravity assists can be substantial. Missions that would otherwise take decades can be completed in a fraction of the time by combining multiple assists. However, these benefits come at the cost of longer and more complex flight paths. Instead of a direct route, spacecraft often follow multi-year trajectories that include several planetary encounters before reaching their final destination. The use of gravity assists also ties directly into transfer windows and orbital alignment. Each assist opportunity depends on precise planetary positions, meaning that mission timing must account for multiple moving targets simultaneously. This interdependence creates highly structured mission plans where departure flybys and arrival are all linked through long chains of orbital events. Beyond practical navigation, gravity assists also illustrate the interconnected nature of the solar system. Planets are not isolated bodies, but part of a dynamic gravitational network where motion can be exchanged between objects. Spacecraft become temporary participants in this system, reshaping their paths through interactions with planetary gravity. As spacecraft move through multiple assists, their trajectories become increasingly complex but also more efficient. Each encounter adjusts their energy state, gradually guiding them toward distant regions of the solar system. These long sequences of maneuvers define many of the longest missions ever undertaken, where travel time is reduced not by speed alone but by strategic use of gravitational interactions. Gravity assists ultimately transform planets into active components of interplanetary travel. Instead of simply being destinations, they become stepping stones that shape the timing and duration of journeys across the solar system. Through these interactions, travel time is not fixed but dynamically adjusted by the geometry of motion and the gravitational structure of space. Propulsion systems define the baseline limits of interplanetary travel time setting, how quickly spacecraft can change velocity, and therefore how efficiently they can move between planetary orbits. In the simplest terms, propulsion determines how much energy a spacecraft can generate to alter its path around the Sun. Because all planets are in constant motion, changing orbits requires not only speed, but also precise timing and direction. The effectiveness of propulsion systems therefore directly shapes whether a mission takes months, years, or even longer. Chemical propulsion, the most widely used system for planetary missions, produces high thrust for short periods. This type of propulsion is typically used during launch from Earth and during key trajectory adjustments in space. It allows spacecraft to escape Earth's gravity and enter heliocentric orbit, but it is not efficient enough for continuous acceleration over long durations. Once initial burns are complete, spacecraft rely on coasting through space, along paths shaped by gravity and earlier velocity changes. Ion propulsion operates differently by producing very low thrust over extremely long periods. Instead of short bursts, it provides continuous gentle acceleration. This method can significantly reduce travel time for certain missions by gradually increasing spacecraft velocity over months or years. Although the acceleration is small, its cumulative effect becomes substantial over long durations, making it useful for deep space exploration, where fuel efficiency and extended operation are essential. Propulsion systems do not act independently of orbital mechanics. Even with powerful engines, spacecraft must still follow trajectories shaped by the Sun's gravity and planetary motion. This means that faster propulsion does not always translate directly into shorter travel times, since optimal paths depend on alignment and orbital geometry. In some cases, higher speed may actually lead to inefficient trajectories that increase total mission duration. The balance between propulsion strength and mission design defines the structure of interplanetary travel. Engineers must choose between faster but fuel-intensive routes and slower but more efficient ones. This trade-off determines not only how long a spacecraft takes to reach its destination, but also how much payload it can carry and how long it can operate once it arrives. Electric propulsion systems extend this balance by enabling long-duration thrusting. These systems use electrical energy often from solar panels or nuclear sources to accelerate charged particles and produce thrust. While the force generated is small, it is highly efficient and can operate continuously. Over time, this continuous acceleration can significantly reshape trajectories, allowing spacecraft to spiral outward or inward through the solar system more gradually. As spacecraft move farther from the Sun, propulsion efficiency becomes increasingly important. Solar-powered systems lose effectiveness in outer regions where sunlight is weak, while nuclear-powered systems maintain consistent energy output. This difference influences mission duration, particularly for journeys to Jupiter and beyond, where long travel times require sustained system performance over many years. Propulsion systems also interact with gravity assists and transfer windows. Even the most efficient engine cannot fully bypass the constraints of orbital alignment. Instead, propulsion is used to refine trajectories within those constraints, adjusting speed and direction at key moments to optimize travel time. This layered approach combines engine power with natural gravitational forces to create efficient paths across vast distances. The limitations of propulsion highlight the fundamental scale of interplanetary space. Even with advanced technology, spacecraft cannot simply accelerate in a straight line toward a planet. They must navigate curved orbital paths where speed direction and timing are continuously adjusted. This structure ensures that travel time is always a product of both engineering capability and celestial mechanics. In long-duration missions, propulsion is often used sparingly after initial departure. Most of the journey consists of coasting phases where spacecraft move along predetermined orbits with only occasional corrections. These corrections are small but critical, ensuring that the spacecraft remains on course over millions or billions of kilometers. Advanced propulsion concepts continue to explore ways to reduce travel time further, but all remain constrained by the same orbital framework. Whether using chemical ion or electric systems, spacecraft are still bound by the Sun's gravitational structure and the motion of planets within it. Propulsion changes the efficiency of travel, but not the fundamental architecture of the solar system. Ultimately, propulsion defines the human capacity to interact with interplanetary space. It determines how quickly spacecraft can adjust their paths, how efficiently they can reach distant worlds, and how long missions must last. Combined with gravity, assist transfer windows and orbital mechanics, propulsion forms one of the core factors that shapes the true duration of travel to every planet. Spacecraft velocity defines how motion unfolds across interplanetary distances, but it is not constant in either magnitude or direction. Every spacecraft moving through the solar system exists within a continuous gravitational field dominated by the Sun, and this field ensures that velocity is always changing along a curved path. Travel time to any planet is therefore not simply a function of speed, but of how that speed evolves under gravitational influence over months or years. At the beginning of a mission, spacecraft velocity is primarily shaped by Earth's orbital motion around the Sun. Once launched, the spacecraft inherits this motion, and then adjust it through propulsion burns and gravitational assists. The resulting velocity places it on an elliptical orbit that intersects the path of the target planet. From that point onward, the spacecraft's speed is constantly modified by the Sun's gravity, increasing as it moves inward and decreasing as it moves outward. In the inner solar system, spacecraft tend to move faster due to stronger solar gravity. As they approach the Sun, their orbital velocity increases, causing shorter travel times over comparable distances. However, this increase in speed is not a simple advantage because reaching inner planets often requires slowing down relative to Earth's orbit rather than accelerating. This creates a counterintuitive situation where higher speeds are needed to adjust orbital energy in specific directions rather than simply reduce travel time. In the outer solar system, velocity decreases as distance from the Sun increases. Spacecraft traveling toward Jupiter, Saturn, Uranus or Neptune gradually slow in orbital motion, even if they maintain constant energy states relative to their transfer orbit. This slowing is a natural consequence of weaker gravitational influence at greater distances. As a result, travel times expand significantly, even when propulsion systems remain active during early phases of the journey. Velocity changes also depend on orbital shape. Most interplanetary missions follow elliptical trajectories where speed varies continuously along the path. Spacecraft move fastest when closest to the Sun and slowest when farthest away. This variation means that travel time is not evenly distributed along the journey. Certain segments of the trajectory may be crossed quickly, while others require long periods of gradual motion. The concept of escape velocity is central to understanding these dynamics. To leave a planet's gravitational influence, a spacecraft must reach a specific threshold speed. However, achieving escape velocity does not guarantee rapid interplanetary travel. Once in solar orbit, the spacecraft's velocity is still governed by the Sun's gravity, which continues to reshape its path and speed throughout the mission. Relative velocity between spacecraft and target planets also plays a crucial role in arrival conditions. Even if a spacecraft reaches the correct distance from the Sun, it must also match the velocity of the destination planet to achieve orbital capture or controlled flyby. This requirement often extends mission duration. A spacecraft may need to adjust speed over long arcs of their trajectory, rather than through single rapid maneuvers. Gravity assists further modify velocity in ways that are not intuitive. A spacecraft can gain speed relative to the Sun without expending fuel simply by passing near a moving planet. This interaction reshapes both direction and magnitude of velocity, allowing missions to reach distant destinations in reduced time. However, these changes are carefully controlled and depend on precise geometry rather than continuous acceleration. Throughout interplanetary travel, velocity is therefore not a fixed quantity, but a continuously evolving state influenced by multiple overlapping forces. Solar gravity, planetary encounters, propulsion inputs, and orbital geometry all contribute to shaping how quickly a spacecraft moves at any given moment. Travel time emerges from this complex interaction, rather than from any single source of motion. The experience of velocity in space differs fundamentally from terrestrial intuition. There is no air resistance or friction to slow motion, only gravitational curvature that constantly redirects movement. As a result, spacecraft can maintain high speeds for long periods while still taking years to traverse the solar system, because distance scales are vast and motion is distributed across curved orbital paths. Ultimately, spacecraft velocity defines the shape of interplanetary journeys rather than simply their speed. It determines how trajectories bend, how long each phase of travel lasts, and how energy is exchanged across gravitational fields. Travel time to every planet is therefore a reflection of how velocity is continuously reshaped by the structure of the solar system itself. Interplanetary travel time is ultimately the result of many overlapping systems acting together within a single gravitational environment. Distance alone does not determine how long a journey takes. Instead, time emerges from the interaction between orbital mechanics, propulsion limits, gravitational assists, transfer windows, and continuously changing velocity. Every planetary mission is therefore a coordinated sequence of movements shaped by the structure of the solar system, rather than a simple path from one point to another. Each planet presents a different timescale of access. Mars requires months, Venus requires a few months, Jupiter requires over a year, and the outer planets require many years of sustained travel. These differences are not only due to distance, but also due to how each orbit aligns with Earth and how efficiently spacecraft can transfer energy between orbital paths. The solar system is arranged in layers of motion, where each layer introduces new constraints on timing and trajectory. Even the concept of arrival is not a single moment but a transition. A spacecraft approaching a planet gradually shifts from solar-centered motion to planetary-centered motion. This shift can take hours during flybys or days during orbital insertion. The boundary between travel and arrival is therefore gradual, defined by changing gravitational dominance rather than a sharp endpoint. Throughout all journeys, the Sun remains the central organizing force. Its gravity defines the structure of every trajectory its radiation influences, spacecraft power systems, and its orbital framework determines all transfer windows. Every planet moves within this system, and every spacecraft must adapt to it. As a result, interplanetary travel time is always measured relative to a dynamic moving reference, rather than a fixed background. Technological capability also shapes travel duration, but only within the constraints of orbital mechanics. Propulsion systems can shorten or extend missions, gravity assists can reshape trajectories, and mission design can optimize energy use. However, none of these factors remove the underlying requirement to follow curved orbital paths through a constantly shifting gravitational field. The solar system imposes a structure that cannot be bypassed, only navigated. As exploration extends farther from Earth, timescales increase in a predictable but non-linear way. The inner solar system is measured in months, the middle regions in years, and the outer edges in decades of planning and execution. This expansion reflects both distance and diminishing energy efficiency, as spacecraft move deeper into weaker sunlight and broader orbital spaces. Despite these vast differences, all journeys share a common structure. Each begins with launch from Earth, transitions into heliocentric orbit, follows a carefully shaped transfer path, and ends with arrival at a moving planetary target. Between these stages, spacecraft spend most of their time coasting through space, following smooth arcs that represent the natural outcome of gravitational motion. Interplanetary travel also reveals that space is not a static environment. It is a system of continuous motion, where every object follows a path shaped by shared forces. Planets orbit spacecraft adjust, and trajectories evolve over time. Travel duration is therefore not an external measure imposed on space, but an expression of how motion unfolds within it. Across all planets in the solar system, time becomes a layered concept. There is launch time, transfer time, waiting time for alignment, and arrival transition time. Each layer contributes to the total duration of exploration. Together they form a complete picture of how humanity moves through the solar system, not as a sequence of short trips, but as long, carefully structured journeys governed by celestial mechanics. In the end, the question of how long it takes to reach every planet has no single fixed answer. Instead, it resolves into a spectrum of durations shaped by position, motion, and energy. Each planet defines its own timescale of access, and together they reveal the true nature of interplanetary travel, a slow, precise, and continuous navigation through a system governed entirely by gravity and motion.